see just said by the chair that the Alan is not able to come over here. I just kind of help him to deliver the talk, and tell you here is from this study is basically is try to using this new type magnetic sensor. This is so-called magnetoelectric sensors. And in this talk, we'll try to discuss about these sensitivities, and this actually those type of sensor is a potential for very low cost magnetic sensors. Well, the collaborator for this work is basically from U.S. Army Research Lab and also Oakland University and Virginia Tech University. Okay. Well, here just kind of the general describe what is the ME sensors. That's basically this is a vector type of sensors, and they have use a very low power and very small size, and the cost can be much lower than this in the futures. And the sensor can be a pretty high sensitivity compared to other type sensors. And the issues, what the talk for today is basically try to address the issue is when at a low frequency, they usually has a very high 1F noise. And the way to overcome this 1F noise is using some of the methods developed by Alan and his group. Okay, and so ideally, in the future, hopefully, there's a sensor cost and sensitivity, and the kind of should be in this corner. So right now, this is kind of the when you have increasing the sensitivity cost usually goes higher, and that's where we have the stand right now. And the principle for this magnetic sensors is quite straightforward. It's using one of the magnetoelectric layers, and that under the magnetic field you have this change of this the magnetoelectric change will cause the change under the magnetic field will changed, and then you have another piezoelectric layer, and that's polarized. Basically, that's the voltage output, and you add these two layers together, you have this the change of the magnetic field will cause the output of voltage. And in the this study here, they are talking about two types of design. One is a symmetry one, that's a layer, and the other one is a symmetry one, that is kind of like a bridge. Okay, well, this is the same thing for all those the type this mechanic type this sensor. They all has a different the resonant frequency. So depending on the driving frequencies, this output can be say have a peak. That means asymmetry is the resonant frequency is somewhere around 130, and the symmetry sensor has a much higher frequencies. And well, asymmetry one has a little bit higher Q. From this graph, you can see this a little bit higher Q than a symmetry one. And in this type of sensor, it's not only depending on the frequency, because you also depending on where you bias the magnetic fields. So here is to show you what is where the bias magnetic field. You can see this is the view graph here. This lambda is basically this strength. Okay, so when you change the change of the magnetic field with the lambda, basically that is this curve. Okay, and then the whole sensor, that's output, will be this curve. That's basically follow these behaviors. So you do need a bias somewhere around here. That's this is amplified. Just kind of enlarged view of this. So you kind of the bias somewhere around here. You have a maximum output. Okay. Oops. Sorry, thanks. Okay, so here the way to overcome this the 1F noise is that you have to able to kind of say modulate using this so-called modulation technique, and modulate so you can shift your frequency to higher frequencies. So that way you have 1F noise will be reduced. So in the case if you shift to the higher frequencies, and then you can clearly see this the baseline is a much about here all the magnitude reduced. Now in the modulation technique here, basically you can use two different type of modulation technique. One is the so-called off resonant. So you just drive the frequency. It's not at the resonant frequencies. And the other one you can drive on the resonant frequency. And you can clearly see that if you drive on the resonant frequency, your output is even higher compared to the off resonance. Okay. And this one, it will be the typical this the response with the biased, and your sensing field is put about micro Tesla and at the 200 hertz, and then you can see that's the output of these sensors. That's basically your sweep range here, and then we can kind of find the right biased, and then we can get the output, higher output. Okay, here is a modulation of the magnetic signal on the symmetry sensors, and this is the signal input is about 0.16, and that's at the 1 hertz. And then you modulate. Basically here, if you modulate at the low, this off resonance, basically off resonance at the 140 hertz, and this is a setup. Basically, you have this is the signal field, that is this one, and then you put this modulator field here, and you do the measurement, and that one, if off modulate, you get this blue curve. Okay, and this one is this is a sideband, what you look for, and basically you can see this is a large, the enhanced of the signal. Now, if you try this is on resonance, and you can see this signal even much higher than this off modulate. Well, in the way that these things is not only the modulator you can deal with, you have to also try to find this is the different bias will cause the different the response of the sensors. So here is to show what is this signal modulator signal on the this symmetry sensors at the signal at 1 hertz, and how this the modulated fields affect this output. And you can see that the modulated field around somewhere around this 0.4 OE, you have a highest output. So you use this technique. Basically, you can see that if you are without modulations, your sensitivity is able to reach is somewhere around the 100 picotesla, and if you do the modulation, you can reach somewhere around 4 picotesla at 1 hertz. Basically, this is at 1 hertz. Well, here just show you this modulations, the magnetic signal for asymmetry sensors, and this at this signal you input is about this signal, and you can see if you use without this direct signal, basically you can see this the output, and that is under this field, right? And when you do the off resonant, then you can see the peak here is much higher than this the peak, so that's about 30 dB. But if you do the on resonant, then this peak is much higher than this peak. That's about 45 dB. Right. But here I think I need to point out this is a little bit tricky here. Is you can see this the sideband for these two, the signal is not equal, and that's the reason it's not equal is because this you drive this resonate is not exactly on this frequency. You are kind of try the resonate exact on these sideband frequencies. So that causes these asymmetries and that much higher output. So you can see the modulation, you can have output about 45 dB and directly is only 25 dBs. Well, and this sensor is not only able to detect this magnetic signal, they are also able to detect this acoustic signal. And the way to detect this acoustic signal is that means that you put this zero bias when you put this zero fields, and you add another this acoustic signal in here, and you just measure the change the bias field. Change this bias field, use a scan, and then you can see this acoustic signal is kind of go reversed to the magnetic signal. Okay, so use this way you can use this sensor kind of do it the dual purpose. One is able to detect the magnetic signal, also can use for detect acoustic signal. Well, here is say this modulation acoustic signal. You can do this even just doing by modulation of the acoustic signal. You can enhance the sensitivities. Okay, and here they show the example that if you direct the signal without the AC magnetic field modulation, then your output is only about 17 dB. Now, if you use under using this modulation field 1.10 E, then you can see this acoustic signal can be about 27 dB. Right. Well, and here you can see that this off the resonate and the on resonate, what is this signal different? Well, in the way you also like to able to adjust this resonant, because the resonant signal is important. So you like to able to adjust this resonant signal, and then you can add this mass or adjust this length. You're able to adjust the stiffness, so that we're able to change the frequency. And in this way, you can change about 20%. So that you can kind of adjust to where the frequency you would like to have. Well, as a summarize, basically in this study, you said demonstrate that one can increasing this operating frequency of the MV, and you can reduce the noise, and you can get again about 2 or 3 order magnitude, and the sensitivity about 4 picotesla per hertz was achieved. And this sensor is a dual acoustic magnetic sensings, and show here is that we use the magnetic field modulation, increasing this signal to noise ratio acoustic signal, and this external restoring this torque allow you to adjust this frequency to where the frequency you like to operate. Well, thank you for your attention.
Thank you. Question? Okay, can I ask a question?
Sure.
Yeah, in the beginning, you showed a 2-layer or 3-layer structure is all by high-class with PCB.
Yes.
But at the end, you showed a tri-layer structure with nickel inside in between the mechanism. What's the function of the nickel?
Function of nickel is to try to enhance, because you try to do the modulations. And so nickel will help to a little bit on that modulation frequency.
Okay, so it's, I see.